Welcome to this lecture called the Capillary Technology Mode of Operation. And at first you can see a capillary, it's filled with water, and if the capillary is removed, you can see the water runs away. And if you put the capillary into the water again, the water rises. As you can see, the surface inside the capillary, it's about 5 millimeter, and you can see the concave surface. And now you can see it in an animation. We have the capillary with a diameter of 5 millimeter, and when you put the capillary into the water rises. And now it's very necessary to understand you have this concave surface because there is negative pressure inside the capillary. This is very necessary to understand, and we show you in the following some examples. Here you can see again the animation, and you can see the green arrows that show you that inside the capillary there is negative pressure. What is negative pressure? We have some examples to show you what is negative pressure. For this you can see 2 containers. They are filled with water. Under the left container is one more container, and we cover this left container, and then the container will be turned, and we put it in the container on the ground, as you can see here. This is very necessary, as I said, to understand the whole technology. Now you can see the container is in the water, and we remove the cover, and the water can't flow out. And in this left container you have negative pressure. In the container on the right side you have hydraulic pressure, and on the left side you have negative pressure. What does that mean? To show what does that mean, we have to drill 2 holes in the containers. As you can see now, there the holes will be drilled, and now let's see what happens. On the right side the water flows out as we all expected, but on the left side we have a sucking action, and air is sucked into the container, and this means negative pressure. Negative pressure means always a sucking action. For this explanation is very, very detailed, but you can say it's the soul of the whole technology. So please remember, negative pressure means a sucking action. And now we have a look at the combination of negative pressure and what happens in a capillary. We come soon to the next pictures. And now you can see again about the pressures inside the containers. Here again the animation, because it's very necessary to understand inside a capillary there is negative pressure. Now we have another view at this. You see the capillary, you see the concave surface of the water, and you see the green arrows which show you there is negative pressure. Now we have a piece of wood swimming in the water, and you can see in the surrounding area of this match there is a little hill. We show it again in this animation. If you have 2 matches inside water, the matches rises, and there you have in the surrounding area of the matches these little hills, And if you take some washing up liquid inside the water, these little hills decrease, and for this the matches rises again. It's very necessary. You can see it in the real attempt. If you put washing up liquid to the water, the floater rises. Now you can see it in the slow motion. It's in the upper right corner. Now there is washing up liquid, and suddenly if the washing up liquid comes into the water, the floater rises. As you've seen in the animation, now it's in reality. Now you know two things. You know, if you have a floater in the water, in the surrounding area of this floater you have a little water hill, and if you put some washing up liquid in the water hills decrease, and so the floaters can rise up. We take a look in the animation again. As you know, if the matches rises, you can see this little water hills in the surrounding area, and if you put some washing up liquid into the water, the matches go up and the water hills decrease. In the next part you can see what happens to this little water hill in the surrounding area of the floater, and as the white arrow shows, the little water hill decreases every time when you put some washing up liquid into the water. As I said, it's a really very, very detailed explanation, but it's very necessary to understand this absolutely. And the explanation is these little water hills causes additional weight. According to the floaters, as you can see here, and as you can see in the footnote, the water hills mean an additional weight that keeps the floaters down, and if the water hills decrease, the floaters rises up a little more. As you can see now, you have some washing up liquid, and with the washing up liquid the water hills decrease, and though the floaters rises again because the weight is away. That's also shown in the footnote. No water hills, no weight, and though the floaters go up again. Now we bring that all together, and at first we have a look what happens in a capillary and what happens if we put a capillary over a floater. We have still this picture. Please take a look at the footnote. Now we have again the real attempt. Take a look at the right upper corner. When you put some washing up liquid into water, the floater rises. And now we couple this with the negative pressure inside a capillary. Here you can see a capillary. The capillary goes down, and when it touches the water rises in the capillary. And now we took the capillary over the floater. And now we can see that the floater goes up, like we put some washing up liquid into the water, but in this case we have no washing up liquid, and now you can see it in the real attempt. You see on the right side the capillary and the floater, and if you put the capillary in the water, the floater rises. You can see on the left side a scale, and it's about 5 millimeter. Now we have the animation again, and we will see why the floater goes up. As we know, there is negative pressure inside the capillary, and this negative pressure means sucking effect, and this sucking effect sucks the water inside the water in the capillary. Let's have a look at the animation. There you can see the negative pressure, which is responsible for the whole effect. And now let's have a look to the consequences. At first, we have one more animation which shows us what really happens. There you have the capillary, you have the negative pressure, and this is again, and soon we will see a stereoscopic picture. And please have a look at the surrounding area of the floaters, and you can see when the water rises in the capillary, the surrounding area decreases. We have it again in another animation. There is the capillary, and now you see the little hills with these black arrows, and when the water rises in the capillary, the little hills become smaller, and with this less weight means the floater rises. And as you can see here, the floater inside the capillary is higher than the floater outside the capillary. And I think I have to apologize for this really very detailed explanation, but at least that's the whole thing. And as you can see again, the floater inside a capillary rises more than a floater outside a capillary, and this is why in the surrounding area you have little water hills, and inside a capillary there is negative pressure, and this negative pressure sucks this little water hills inside the water. As you can see in a stereoscopic picture, please have a look at the water hills, and you can see the water hill inside the capillary is much smaller than the water hill outside the capillary. At least, again, because, as I said, it's the whole thing. And now, it's very interesting to see what does that mean, because that's not very sensational to this point, but at least you will see it's a very interesting effect. We have it again, you see the weights and the decreasing weights according to the floater inside the capillary. And I hope now you understand why does a floater inside a capillary rises higher than a floater outside a capillary. See it again in the footnote. You have different weights, and with this, the floater inside the capillary rises more than a floater outside a capillary. For this, you have again a stereoscopic picture. It's very necessary to understand, so it comes again and again. You see the surrounding area of the floaters, and the water hill according to the floater inside the capillary decreases, and on the other hand, the water hill according to the floater outside the capillary doesn't decrease. And now you can see it in the real attempt again. If you put the capillary in the water, the floater rises, and at least you can have a look at these water hills, and as you can see, the water hill according to the floater outside the capillary doesn't decrease. With this, our floaters are now some cubes, and as you can see in the animation, you can change these cubes, as you can see, from the floater inside the capillary to the floater outside the capillary, and for this you have a circulation, and now you have a problem with the energy conservation because of the frictional heat. The water has to become warmer, and on the other hand, you got some energy from the moving of the floaters. And for this, the energy conservation doesn't work in this case. Let's have a look what can happen in the following. We change the cubes faster and faster, and at least we got a wheel, as you can see now. You see the water hills again, you see this wheel, and now we show again what happens if we put a capillary to this system, and you have to put the capillary inside the water, and the water rises, and when the water rises, the water hill inside the capillary decreases. And please realize, we are not talking about capillaries and water and wheels, we are talking about the energy conservation. And as you can see, when the wheel starts to rotate, you have a problem with the energy conservation because of the friction heat. The water becomes warmer, and if the water becomes warmer and the wheel is rotating, you can't use the energy conservation. We come back to our animation. As I apologized, we always show you the same pictures, but at least we are talking about the energy conservation, and for this, again and again, now we have the capillary, we put the capillary inside the water rises, and the water hills inside the capillary in the surrounding area of the wheel decreases, and for this, the wheel will start to rotate at least. As you can see, the water hill outside the capillary is much bigger than the water hill inside the capillary, and for this, more weight is on the right side, and for this, the wheel has to start to rotate. It's not a decision of the wheel, that's because of the facts. We come back to our picture with the water hills in the animation, and back to the cubes, and now we hope you understand these pictures. Now we are in the reality, and you see the cubes on the floater on the left side, and the cubes now come to the right side, and as you see, the floaters are doing the same as you have seen in the animation. And there you can see the cube inside the water, the cube is moved, and now you see there is a disc, and the cube rises up to the disc. See it shown by the white arrow, and the floater inside the capillary rises. That's the same thing. Now you can see it very clearly. When the cube is on the disc, the floater rises. Here, see it again. And same with the second cube. You can see the distance according to the floaters are exactly like it was shown in the animation. And now we have second cube. Second cube touches the disc and the floater rises. Now you can see it in the cut, and there you can take the letters in the background to see that the difference is exactly like in the animation. Here again in the cut. And as you can see, the energy conservation is ineffective in this case because of the frictional heat and the moving of the floaters. As you can see again here in the animation, you know why the floater inside the capillary is higher than the floater outside the capillary, and though you can change the cubes, here you can see again why is this so, and you know there is a water hill, that means a weight according to the floater. And now we come again to this picture. I promise it's the last time, but I hope you understand this quietly and correctly. And please let me say again, you see the two water hills, that means weight, and when the water went up inside the capillary, the weights become smaller, and with this the floater inside the capillary rises. And you can see it also in the footnote again. You have different weights, and with this the floater rises. This is so far so good, and now we have some other interesting news. Here again, attempt with the floater and the capillary. It's in slow motion. Please have a look at the left side. There is a scale, and this is shown to you to remember and to prove that a floater really rises in a capillary. And now we change the water with a ferrofluid. A ferrofluid is a magnetic fluid, and we have the problem with the capillary. It's very small. A capillary has a diameter from 5 millimeter, but when we use a ferrofluid, we can have a tube maybe 1 meter or 5 meter or 50 meter. You need a magnetic ring, magnetic wheel, and you see this tube, and this tube is not 5 millimeter, maybe it's 5 meter, but the effect is the same. Because the ferrofluid is magnetic, and there you have a ring magnet, and you bring the ferrofluid with this ring magnet into the tube, as you can see now, and with this you can build it as big as you want. As I said, this tube can have a diameter of 100 meter or maybe of 3 miles. It's a question how big you want to build this, but the effect at least is the same. When the ferrofluid rises inside the tube, the magnetic ferrofluid hill decreases, as you know from the water examples. And as you see here, you have a capillary with a diameter of 5 millimeter, and you have a tube with a diameter maybe of 5 meter or as big as you want. And with this, you can generate so much energy as you want. The principle is the same. We have a negative pressure inside the tube, and this negative pressure sucks, in this case, the ferrofluid hill inside the ferrofluid, and with this you have the same effect. Means that there is more weight on the right side than on the left side, and with this wheel has also to start to rotate. Here again, in kind of slow motion, you can see the ring magnet is moved down, and at least the ferrofluid rises up inside the tube, and the more the ferrofluid rises up, the more the ferrofluid hill decreases. And for this, the magnetic wheel starts to rotate, and you can generate energy as much as you want. As I said, it's the same principle as you have seen the beginning of the video, and as you can see, you have a rotating wheel, but in this case you can mark out how big this wheel should be. With this you can mark out how much energy you want to create. As you see, the wheel is rotating, and you know why? Because of the more white on the right side than on the left side. There is a picture from fluid magnetic technique. There you can see it again, and at least it's a real picture. The magnet and the holder, and you can see the ferrofluid, which is like in the animation. At least we hope you enjoyed this lecture, and if you have any questions, please contact us. You will see the contact at the end of the video, and we want that you maybe give us an answer what is with the energy conservation, and at least one more picture from the rising floater. And for this, thank you, and we hope to see you again. Goodbye.